Welcome to qnawire.
We can apply the conservation of linear momentum here first and say that P initial equals P final. And so this would give us mv equaling the sum of the masses times the velocity of the center of mass final. And so the final velocity of the center of mass would be equaling mv over the sum of the masses. Of course, here capital M would be the mass of the thin rod, and then lowercase m would be the mass of the clay ball. And we can say that the y position of the center of mass, we can find this. This would be the mass of the clay ball multiplied by L over 4 plus the mass of the thin rod times 0 divided by, again, the sum of the masses. And so this would be equaling ml over 4 times m plus m. And the distance, we would say the y position of the clay ball with respect to the center of mass, this would be 1/4 times L minus the y position of the center of mass. This would be equaling, we could say, L over 4 minus ml over 4 times m plus m. And this is giving us the mass of the thin rod divided by 4 times m plus m. So essentially, we can then find the moment of inertia for the rod, and we're going to use the parallel axis theorem, and we're going to treat it as a point mass. So we can then say that the moment of inertia of the rod would be equaling the moment of inertia through the center of mass, 1 over 12 ml squared. This is a tabulated equation, essentially, plus the mass of the rod times the mass of the clay times L divided by 4 times m plus m quantity squared. And so we can then say that we're going to apply the observation of angular momentum about the system's center of mass. So L initial equals L final, applying again the conservation of angular momentum. This is giving us mvy of the clay. This would equal the moment of inertia for the rod plus the moment of inertia for the clay multiplied by the final angular velocity. And so the final angular velocity would be equaling the mass times velocity times y sub clay divided by the moment of inertia for the rod plus the moment of inertia for the clay. And then we can substitute a little bit higher. So this would be the mass times the linear speed times the y position of the clay with respect to the center of mass. And then this would be multiplied by ml squared over 12 plus the mass times ml divided by 4 times the sum of the mass quantity squared plus the mass of the clay times the y position of the clay squared. And so we can simplify a bit and say the final angular velocity would be equaling mv times m times L over 4 times the sum of the mass. We're essentially just plugging in for the y position of the clay. And so we can then divide this by ml squared over 12. And then this would be plus m times ml over 4 times the sum of the masses quantity squared plus the mass of the clay multiplied by ml over 4 times the sum of the masses quantity squared. And the final angular velocity is then equaling 12 mv times the sum of the masses divided by L multiplied by 7m squared plus 11m times m, the mass of the clay times the mass of the rod, plus 4 times the mass of the rod squared. And we can simplify further. This would be 12 times m times v divided by the length of the rod times 7 times the mass of the clay plus 4 times the mass of the rod. This would be our final answer for the final angular velocity. That is the engine. Thank you for